Tonight we drift through a region of space so extreme that even imagination struggles to keep up. Ahead of you hangs a darkness unlike any darkness you have ever known. It is not the darkness of night, not the darkness behind closed eyes, not even the darkness between distant stars. This darkness has weight. It has gravity. It pulls on the fabric of reality itself. You float silently above a glowing sea of galaxies. Billions of stars shine beneath you like scattered grains of silver dust. Vast cosmic clouds stretch across unimaginable distances. Entire galactic civilizations, if any exist, would spend millions of years crossing the regions you now glide over in moments. And yet none of those colossal structures command your attention. Something else does. Far ahead, occupying the center of your view, is a black hole so enormous that comparison becomes almost meaningless. Its name is TON 618. Even among black holes, it is a monster. You watch a ring of brilliant light swirling around it. The ring twists and bends in impossible ways. Light from galaxies behind the black hole curves around the darkness, producing glowing arcs suspended in space like celestial brushstrokes. The sight is beautiful. It is also unsettling, because somewhere beneath that radiant halo lies an invisible boundary known as the event horizon, the point beyond which nothing can return. Not light, not matter, not messages, not stories. At least as far as current physics can tell. And that is where tonight's mystery begins. What truly happens to something that falls into a black hole? The question sounds simple. Scientists have asked it for decades. Yet despite all our equations, telescopes, satellites, and supercomputers, nobody possesses a complete answer. Some mysteries are difficult because we lack information. This mystery is difficult because the universe itself may be hiding the information. Before we continue, though, there is one important survival procedure to complete. Fortunately, it is much easier than escaping a supermassive black hole. So, before you get comfortable, take a moment to like the video and subscribe. But only if you genuinely enjoy what I do here. And while you're here, leave a comment telling everyone your location and local time. It's always remarkable to see people gathering from all around our small planet to explore enormous cosmic questions together. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. The first thing you notice as you approach TON 618 is scale. Human beings are not naturally equipped to understand scale beyond everyday experience. A mountain feels large. An ocean feels vast. A planet seems almost incomprehensibly enormous. Then astronomy arrives and politely informs you that Earth could fit inside the sun over 1,000,000 times. After that, astronomy becomes considerably less polite. The sun itself is merely one ordinary star among hundreds of billions inside the Milky Way. The Milky Way is one galaxy among hundreds of billions in the observable universe. And TON 618? TON 618 sits in an entirely different category. Scientists estimate that it contains tens of billions of times the mass of our sun. It belongs to a class known as ultramassive black holes, objects so large that even supermassive black holes begin to look modest by comparison. That is an established scientific fact. Yet the surprising observation is this. Despite being one of the largest known black holes, TON 618 was not initially discovered because scientists were searching for a giant black hole. It first appeared as a brilliant quasar. A quasar is a dazzling beacon powered by matter falling toward a black hole. As gas spirals inward, it heats to extraordinary temperatures and emits tremendous amounts of energy. In some cases, A quasar can outshine entire galaxies. Imagine noticing a campfire from across a continent and only later realizing the fire is actually sitting atop a mountain larger than a nation. That is roughly the level of surprise involved. You continue drifting closer. The glowing disk surrounding Tian 618 stretches across distances that make solar systems seem tiny. Streams of matter whirl around the darkness at significant fractions of the speed of light. Everything appears peaceful from afar. But gravity is quietly at work. Gravity here does not behave as a force in the ordinary sense. According to modern physics, gravity emerges because mass bends spacetime itself. You can picture spacetime as an invisible landscape. Planets create gentle valleys. Stars create deeper ones. Black holes create something closer to a cosmic waterfall. Near Tian 618, the waterfall becomes almost vertical. You imagine dropping a clock toward the black hole. To the clock, time feels normal. Tick, tick, tick. But from your distant viewpoint, something strange occurs. The clock appears to slow. Its seconds stretch. Its movement becomes sluggish. As it approaches the event horizon, it seems almost frozen. This effect is called gravitational time dilation, one of the most fascinating predictions of Albert Einstein's theory of relativity. And remarkably, experiments have repeatedly confirmed that gravity truly affects the passage of time. The stronger the gravity, the slower time flows. Near Tian 618, the effect becomes extraordinary. A traveler descending toward the black hole could experience time very differently from someone watching from afar. The universe, it seems, does not provide a single universal clock. Already, reality feels stranger than fiction. And yet we have barely begun. As galaxies slide silently past, you notice something else. The black hole itself remains invisible. You cannot see its surface. You cannot see its interior. You cannot even be certain what exists at its center. Physics predicts a singularity, a point where density becomes effectively infinite and known equations break down. But many scientists suspect that our current theories are incomplete. The singularity may be real, or it may be evidence that deeper laws remain undiscovered. That unresolved mystery sits at the heart of every black hole. The closer we look, the less certain we become. You continue approaching the colossal shadow. The light around it bends into luminous circles. Background galaxies appear distorted. Space itself seems twisted. The universe behaves as though someone has quietly rewritten the rules. And perhaps, in a sense, that is exactly what has happened. Because black holes occupy a unique place in science. They are not merely objects. They are laboratories. Natural experiments conducted on scales impossible to reproduce anywhere else. Inside them, gravity reaches its ultimate extremes. Inside them, quantum physics may collide with relativity. Inside them, some of the deepest secrets in existence may be waiting, or hidden forever. For now, you remain outside the event horizon, safe, curious, suspended above a darkness larger than understanding. And as Tian 618 slowly grows in your field of view, one thought follows you through the silence. If the biggest black hole ever discovered can exist at all, what kind of universe created it? The question follows you as you drift beside the immense shadow of Tian 618. What kind of universe creates something this large? The black hole remains ahead, wrapped in its luminous halo of infalling matter. From this distance, it almost resembles a dark eye staring through cosmic time. Around it, entire galaxies move through the darkness like drifting lanterns. You continue forward but slowly. This is not a journey measured in kilometers. It is a journey measured in ideas. To understand the biggest black hole ever discovered, you first need to understand how humanity learned that black holes could exist at all. And strangely enough, the story begins long before anyone knew what a galaxy was. Far below, the stars seem motionless. Yet every one of them carries a history. You imagine yourself standing in the 18th century. Telescopes are small. The universe appears modest. Most people believe the stars fill a relatively limited cosmic realm. Then an English natural philosopher named John Michell begins wondering about gravity. In 1783, Michell proposes an extraordinary possibility. What if a star became so massive that its escape velocity exceeded the speed of light? If light could not escape, the star would become invisible. A dark star. The idea sounds surprisingly modern. Yet Michell had no theory of relativity, no knowledge of galaxies, no understanding of spacetime. He was simply following mathematics where it seemed to lead. For generations, the concept remained mostly speculative. Then the 20th century arrived, and reality became much stranger. You watch distant galaxies drift through space while another figure enters the story. Albert Einstein. In 1915, Einstein introduces general relativity, a theory that transforms gravity from a force into geometry. Space and time become part of a single fabric. Mass tells spacetime how to curve. Curved spacetime tells matter how to move. It is one of the most successful scientific theories ever developed. An established scientific fact is that general relativity has passed countless experimental tests over more than a century. And yet Einstein himself was uncomfortable with some of its implications, because hidden inside his equations was something peculiar. If enough mass were compressed into a sufficiently small region, spacetime could collapse inward. An event horizon could form, a boundary beyond which escape becomes impossible. Not long afterward, physicist Carl Schwarzschild found an exact solution to Einstein's equations while serving during World War I. His calculations described what we now call a Schwarzschild black hole. At the time, many scientists viewed the result as a mathematical curiosity. Nature surely would not create such bizarre things. At least that was the assumption. The universe had other plans. You continue gliding through darkness. Ahead, the glow around TON 618 brightens. The quasar's light stretches across intergalactic distances, reaching places unimaginably far from its source. That light carries a message. It tells a story of matter falling inward. A story scientists would eventually learn to read. The surprising observation is that black holes were once considered absurd. Today they are considered ordinary. Astronomers now believe that most large galaxies contain supermassive black holes at their centers, including our own. Deep within the heart of the Milky Way resides Sagittarius A*, a black hole containing millions of solar masses. Compared with TON 618, however, Sagittarius A* looks almost modest. That comparison alone reveals how enormous the cosmic scale has become. You imagine shrinking the solar system until it fits inside a marble. Even then, TON 618 would remain staggeringly large relative to many other known black holes. And this raises another puzzle. How do black holes become so massive? The simplest answer seems straightforward. A star collapses. A black hole forms. It absorbs matter. It grows. But when astronomers examine the early universe, things become complicated. Very complicated. Light takes time to travel. When telescopes observe distant objects, they are also observing the past. Some quasars appear only a few 100 million years after the Big Bang, yet they already contain enormous black holes. Some seem far too large to have grown through ordinary processes in the available time. It is as if you planted a seed yesterday and discovered a forest this morning. The numbers do not fit comfortably. Scientists continue investigating possible explanations. Perhaps the first stars were much larger than expected. Perhaps black holes formed directly from giant clouds of gas. Perhaps multiple growth mechanisms operated simultaneously. Evidence exists for several possibilities. No single answer has completely solved the mystery. And so the story continues. You pass through a region where galaxies become sparse. The distances between them feel almost unsettling. Popular images often show the universe crowded with stars and glowing nebulae. Reality is far emptier. Space is mostly nothing. Vast expanses separate even neighboring galaxies. If atoms were enlarged to the size of cathedrals, much of ordinary matter would still be empty space. The universe seems to enjoy repeating that pattern on every scale. Plenty of room. Very little substance. And yet somehow, within all that emptiness, gravity gradually builds structures. Stars. Galaxies. Clusters. Superclusters. Black holes. It is like watching invisible currents shape an ocean no one can directly see. This leads naturally to another remarkable discovery. Much of the universe may consist of something we have never identified. Dark matter. Astronomers observe galaxies rotating too quickly for visible matter alone to explain. Additional mass appears to be present. Something unseen exerts gravitational influence. An established fact is that dark matter has never been directly observed in laboratory experiments despite decades of searching. Its existence is inferred through gravitational effects. You cannot see it. Yet galaxies behave as though it surrounds them. This invisible component may have helped giant structures form more rapidly after the Big Bang. If so, it may also have played an indirect role in creating colossal black holes. The mystery deepens. Every answer seems connected to another unanswered question. As you drift onward, TON 618 fills more of the cosmic horizon. Its gravitational influence stretches across enormous distances. Light bends around it. Matter spirals toward it. Time itself behaves differently nearby. And the deeper you travel into the history of black holes, the clearer one truth becomes. Humanity did not discover black holes because we understood the universe. We discovered them because the universe repeatedly surprised us. Again and again. First with dark stars. Then curved spacetime. Then event horizons. Then quasars. Then monsters like TON 618. Each revelation expanded the boundaries of knowledge. Each revelation uncovered a larger mystery waiting beyond. And now, as the giant shadow grows before you, another realization emerges from the darkness. Perhaps the biggest challenge is not explaining how black holes behave. Perhaps the bigger challenge is explaining how the universe learned to build them so quickly in the first place. That question waits ahead, hidden somewhere beyond the glow. The glow ahead intensifies. What first appeared as a distant beacon now dominates the darkness around you. The brilliant quasar surrounding TON 618 spreads across space like a cosmic storm frozen in time. Streams of gas whirl inward. Radiation pours outward. Gravity quietly controls everything. You have spent ages, at least in the imagination of this journey, approaching the largest known black hole. Now you begin to appreciate just how extraordinary it truly is. The name itself sounds strangely modest. Ton 618. Not the devourer. Not the abyss. Not the emperor of darkness. Astronomy often gives its greatest wonders names that sound suspiciously like inventory labels. Somewhere in the universe exists a black hole capable of swallowing entire solar systems, and humanity essentially tagged it with something resembling a warehouse barcode. The cosmos, apparently, has little interest in marketing. Ton 618 was first catalogued in a survey of faint blue objects during the mid-20th century. At first, astronomers did not realize exactly what they were looking at. What they saw was an incredibly bright quasar. Only later did careful observations reveal the astonishing engine responsible for that brightness. At its center lurked one of the most massive black holes ever identified. An established scientific fact is that TON 618 is estimated to contain tens of billions of times the mass of the Sun. Different measurements produce somewhat different values, but all place it among the most massive black holes known. Even saying those numbers feels inadequate. Human intuition breaks under quantities like these. So instead of numbers, imagine scale. Suppose the Sun were reduced to the size of a single grain of sand. The Earth would become microscopic. Jupiter would barely be noticeable. The entire solar system would shrink dramatically. Yet TON 618 would still represent a mountain of mass compared with that tiny grain. The comparison remains imperfect because the true scale exceeds ordinary visualization. As you drift closer, the quasar's disk becomes more detailed. Matter races around the black hole at enormous speeds. Friction heats the swirling gas to incredible temperatures. The resulting radiation shines across billions of light years. Ironically, black holes themselves emit no light. Some of the brightest objects in the universe are powered by things that are completely dark. The contrast feels almost poetic. You cannot see the black hole. You see everything happening around it. Like hearing the roar of a waterfall hidden behind a cliff. The water reveals what the cliff conceals. The same principle applies here. The surrounding chaos announces the presence of the invisible giant. And what a giant it is! You begin a thought experiment. Imagine replacing the black hole at the center of our Milky Way with TON 618. Would Earth be swallowed immediately? Surprisingly, no. This is one of the strangest truths about black holes. Their danger depends heavily on distance. If the Sun were somehow replaced by a black hole of equal mass, Earth's orbit would remain nearly unchanged. The planet would become cold and lifeless without sunlight, but gravity would continue acting much as before. Mass determines gravitational influence far more than appearance. The surprising observation is that many people imagine black holes as cosmic vacuum cleaners, endlessly sucking everything nearby into oblivion. Reality is subtler. A black hole's gravity behaves normally at large distances. You could orbit one safely if you remained far enough away. Of course, far enough away becomes an interesting concept when discussing something as enormous as TON 618. The region surrounding it extends across truly staggering distances. Its influence dominates vast portions of its host galaxy. As you continue your approach, stars begin appearing distorted. Not because the stars themselves are changing, because space between you and those stars is bending. Einstein predicted this effect more than a century ago. Massive objects warp spacetime. Light follows those curves. The result is gravitational lensing. Galaxies behind TON 618 appear stretched into arcs and rings. Some images seem duplicated. Others appear shifted from their true positions. The universe becomes a hall of mirrors constructed from gravity. You watch a distant galaxy bend around the black hole's edge. Its light travels billions of years across space only to have its final path altered by the monster before you. That journey contains an astonishing implication. Every photon reaching your eyes has survived an epic voyage. Many began traveling long before Earth existed. Some departed their galaxies before the solar system formed. Now, after crossing immense cosmic distances, they encounter TON 618 and curve around its gravitational well. Light itself becomes part of the story. And yet an unresolved mystery remains. How did something this large form at all? The question grows more troubling the closer you examine it. Black holes can grow through accretion, gradually consuming nearby gas. They can also merge with other black holes. Astronomers have directly observed black hole mergers through gravitational waves, ripples in spacetime first detected in 2015. That discovery confirmed another major prediction of general relativity. But even when these growth mechanisms are included, some ultramassive black holes seem uncomfortably large, especially in the early universe. Some researchers propose that enormous seed black holes formed directly from collapsing primordial gas clouds. Others investigate whether unusual conditions after the Big Bang accelerated growth rates. Still others wonder whether unknown processes remain undiscovered. Evidence supports parts of several ideas. No consensus explains every observation. The mystery persists. And TON 618 stands as one of the strongest reminders. The giant black hole almost feels less like an answer than a question written across cosmic scales. You continue drifting. The accretion disk glows beneath you like a whirlpool of liquid fire. Temperatures rise into millions of degrees. Magnetic fields twist violently. Jets of energetic particles may extend enormous distances into surrounding space. The environment would instantly destroy any spacecraft humanity could currently build. Fortunately, tonight's journey belongs to imagination. Otherwise, this would be an extremely short bedtime story. You arrive near the outer regions of the glowing disk. Here the motion becomes easier to appreciate. Gas does not simply fall inward. It spirals, orbit after orbit, like water circling a drain, except the drain spans distances larger than planetary systems. Every orbit converts gravitational energy into heat. Every collision releases radiation. Every moment adds to the quasar's brilliance. And somewhere beneath all that light lies the event horizon, the boundary that separates observation from mystery. Crossing it changes everything. Outside the horizon, physics still provides guidance. Inside, certainty begins to fade. Scientists can calculate much about black holes. They can estimate masses, measure spin, observe surrounding matter, track gravitational effects. Yet the interior remains hidden. The biggest black hole ever discovered contains a region forever shielded from direct observation, a place where information may behave in ways we do not fully understand, a place where known theories may eventually fail. As the glowing disk rotates beneath you, another thought quietly emerges. Perhaps the most remarkable thing about TON 618 is not its size. Perhaps it is the fact that even an object this enormous remains, in its deepest nature, profoundly mysterious. And the closer you move toward the event horizon, the stranger that mystery becomes. You move closer still. The luminous disk of TON 618 now surrounds much of your view, a vast river of incandescent matter circling a darkness that refuses to reveal itself. The black hole remains invisible. No matter how long you stare, there is nothing to see directly. Only consequences. Only bent light. Only distorted time. Only gravity. And perhaps that is fitting. Some of the most important things in the universe are known only through their effects. You never see gravity itself. You see apples fall. You see planets orbit. You see galaxies rotate. Likewise, you never truly see a black hole. You see spacetime responding to its presence. Ahead lies the event horizon, the famous boundary beyond which no signal can return. The phrase sounds dramatic, but its scientific meaning is surprisingly precise. The event horizon is not a wall, not a surface, not a glowing barrier. If you crossed it, you would not strike anything. You would not hear an alarm. No cosmic sign would flash overhead announcing, "Congratulations, you have entered the point of no return." The universe is rarely that theatrical. Instead, the horizon is a geometric boundary in spacetime, a location where all future paths lead inward. An established scientific fact is that, according to general relativity, once an object passes beyond the event horizon, every possible future trajectory carries it toward the black hole center. Escape ceases to be a matter of speed. There is simply no outward route remaining. You imagine floating toward that boundary. From your perspective, nothing unusual occurs at the exact crossing point, assuming the black hole is sufficiently large. And TON 618 is certainly large. In fact, one of the strangest consequences of its immense size is that the event horizon may be relatively gentle compared with those of smaller black holes. This sounds completely backwards. Many cosmic truths do. People often imagine a black hole's edge as a place of immediate destruction. Yet near an ultramassive black hole, tidal forces at the horizon can be surprisingly weak. Tidal forces arise because gravity changes with distance. Your feet experience slightly different gravity than your head. On Earth, the difference is tiny. Near a black hole, it can become enormous. For smaller black holes, those differences become lethal before you even reach the horizon. The process has acquired one of the more memorable names in physics: spaghettification. Yes, among all the profound concepts developed by theoretical physics, one of them essentially translates to "you become cosmic pasta." Science occasionally enjoys a good joke. As gravity stretches you lengthwise and compresses you sideways, the effect becomes increasingly extreme. But TON 618 changes the situation. Because its horizon is so vast, the gravitational gradient there is less severe. A hypothetical traveler might cross the event horizon without immediately noticing anything dramatic. That possibility remains one of the most unsettling ideas in astronomy. Imagine passing a boundary from which escape is impossible, and not realizing it. You continue drifting. The horizon grows near. Light around you behaves strangely. Stars behind the black hole appear warped into glowing rings. Some seem duplicated. Others vanish entirely. The sky itself looks broken. A photon leaves a distant galaxy. It travels for billions of years. Then, near TON 618, its path bends sharply. To an outside observer, gravity appears to sculpt the cosmos like a giant invisible lens. You follow one such photon in your imagination. The particle has no experience of time. This is one of the surprising consequences of relativity. For a photon traveling at light speed, the interval between emission and arrival effectively collapses. A beam of light crossing billions of years experiences no journey in the way we normally think of one. From the photon's perspective, if such a perspective could exist, the trip is instantaneous. The implication feels almost impossible. The universe appears vast beyond comprehension. Yet light itself experiences that vastness differently. Space and time refuse to behave according to common sense. The closer you approach TON 618, the clearer that becomes. You reach the edge of the shadow. Now another mystery emerges. What exactly happens to time near a black hole? You remember the clock from earlier, the one slowly descending toward the horizon. To a distant observer, the clock appears to slow dramatically. Its ticks become farther apart. Its image reddens and fades. Eventually, it seems frozen at the edge, never quite crossing, never quite disappearing. Yet from the clock's own perspective, time continues normally. The traveler crosses the horizon. The journey proceeds. Both descriptions are valid. Neither observer is mistaken. Reality accommodates both viewpoints simultaneously. This is not speculation. It emerges directly from the mathematics of relativity, and it challenges one of humanity's deepest assumptions, that time flows identically for everyone. The universe disagrees. Time is local, flexible, dependent upon motion and gravity. Near TON 618, that flexibility becomes extraordinary. You begin another thought experiment. Suppose you spend a period orbiting close to the black hole. When you eventually return to distant space, far more time may have passed elsewhere. Friends would age. Civilizations could rise and fall. Continents might change. Entire eras of history could unfold. You would emerge into a future that arrived while you were away. This is not science fiction. Time dilation has been measured repeatedly with clocks on airplanes, satellites, and spacecraft. Near black holes, the effect simply becomes far more dramatic. Yet an unresolved mystery waits beneath all these established facts. General relativity describes gravity beautifully. Quantum mechanics describes the microscopic world with astonishing precision. Both theories work. Both have been confirmed countless times. Yet when scientists attempt to combine them inside a black hole, trouble appears. The equations become incompatible. Theories begin breaking down. The singularity predicted at the center represents more than an exotic location. It signals a limit of current understanding. Many physicists suspect that a deeper theory remains undiscovered. Perhaps quantum gravity. Perhaps something even stranger. Whatever the answer, the heart of a black hole may contain clues. Not merely about black holes, about reality itself. You drift just above the horizon. The darkness beneath you feels less like an object and more like an absence. A missing piece of the universe. Everything nearby moves according to its influence. Nothing reveals what lies within. The contradiction is remarkable. TON 618 may be among the largest known objects of its kind. It exerts enormous influence across cosmic distances, and yet its interior remains fundamentally hidden. The bigger it becomes, the more mysterious it seems. You look into the darkness. The horizon stretches endlessly. No signal emerges. No image returns. No observation penetrates beyond. Only theory follows. Only mathematics ventures farther. And somewhere beyond that invisible boundary, a question waits. Not merely what happens to matter. Not merely what happens to time. But what happens to information itself. Because if something falls into a black hole forever, Does the universe remember? Or can reality truly forget? That puzzle lies ahead, deeper than gravity, deeper than the horizon, deeper than the darkness itself. The question lingers in the darkness. Does the universe remember? You hover at the edge of the event horizon of TON 618, staring into a region that no observation can directly reach. The glowing accretion disk continues its endless rotation behind you. Ahead lies only shadow. Yet the shadow is not empty. It contains one of the greatest puzzles in all of science. To explore it, you must venture farther than any telescope can see. Not physically, only through thought. Fortunately, thought experiments are among humanity's most powerful tools. Einstein used them. Generations of physicists used them. Tonight, drifting beside the largest known black hole, you use them too. Imagine that you carry a small notebook. Inside are simple observations, a star chart, a favorite recipe, perhaps a reminder not to park a spaceship too close to a black hole. That particular note could save considerable inconvenience. You cross the event horizon. Nothing dramatic happens at first. No explosion. No flashing lights. No invisible cosmic customs officer checking documents. Space remains dark. Time feels normal. You continue inward. And that is precisely what makes the situation so unsettling. The horizon itself does not announce its importance. Only later do you realize what has changed. Every possible future now points deeper into the black hole. Escape has become impossible. Not because your engines fail. Not because gravity is pulling especially hard in a particular direction. Because the structure of spacetime itself has changed. Outside the horizon, future paths can lead outward. Inside, they cannot. The geometry of reality has quietly closed behind you. This is one of the strangest consequences of general relativity, and it remains an established scientific prediction of the theory. As you descend farther, the notebook remains with you. Its information still exists. The star chart remains printed on the pages. The recipe remains readable. Every detail appears preserved. So where is the problem? The problem arrives later, far later, from the perspective of an outside observer, because black holes do not simply sit in silence forever. In 1974, physicist Stephen Hawking discovered something astonishing. When quantum mechanics is applied near an event horizon, black holes should emit a tiny amount of radiation. Today we call it Hawking radiation. The prediction shocked the scientific world. Black holes were supposed to absorb things, not glow, not evaporate, not slowly disappear. Yet the mathematics suggested otherwise. An established scientific fact is that Hawking radiation remains one of the most important theoretical predictions connecting gravity and quantum physics, although it has not yet been directly detected from astrophysical black holes because the effect is far too weak. For a giant like TON 618, the process would be extraordinarily slow. So slow that words such as slow become almost meaningless. Long after every star in its galaxy dies. Long after galaxies themselves change beyond recognition. TON 618 would still exist. Its lifetime would stretch across timescales so enormous that ordinary history becomes microscopic. But eventually, according to current theory, even a giant black hole would evaporate. And here the paradox appears. Suppose your notebook fell inside. Suppose the black hole later evaporates completely. What happens to the information? The notebook contained data. The arrangement of atoms mattered. The details mattered. Physics normally insists that information is conserved. The universe can rearrange information, transform it, scatter it, but fundamental laws suggest it should not simply vanish. Yet black holes seem capable of exactly that. The notebook enters. The black hole evaporates. The notebook is gone. The information appears lost. Forever. This conflict became known as the black hole information paradox. And for decades it has troubled physicists. You drift deeper into the thought experiment. Imagine gathering every page ever written, every song, every photograph, every memory recorded by every civilization that has ever existed. Now imagine dropping it all into a black hole. Would reality truly allow all that information to disappear? The surprising observation is that many physicists believe the answer is no. Information should survive somehow. The challenge is determining how. Various possibilities have emerged. Some researchers propose that information becomes encoded on the event horizon itself. Others suggest subtle correlations within Hawking radiation. Still others investigate ideas involving holographic descriptions of spacetime. One particularly influential concept is the holographic principle. The idea sounds almost unbelievable. Certain calculations suggest that information describing a three-dimensional region may be representable on a two-dimensional boundary. Like a hologram. Like a cosmic projection. Evidence from theoretical physics has made this concept increasingly important, though many details remain actively studied. If true, the event horizon may function less like a one-way door and more like an unimaginably sophisticated information archive. Reality might record everything that falls inward, not in a form we readily recognize, but in a form that survives. The mystery remains unresolved. Yet the implications are profound, because the paradox touches something deeper than black holes. It touches the nature of reality itself. What does it mean for information to exist? What is a memory? What is a physical record? Why should information be conserved at all? Questions that initially seemed technical suddenly become philosophical, and they emerge naturally from staring into a hole in space. The farther you descend into imagination, the stranger the landscape becomes. The singularity waits ahead. Or perhaps it does not. Many physicists suspect that the singularity predicted by classical relativity represents a warning sign rather than a literal destination. Infinite density often indicates that a theory has reached its limits. Just as older maps sometimes marked unexplored regions with sea monsters, modern equations occasionally produce infinities where understanding runs out. A future theory of quantum gravity may reveal a very different picture. Perhaps spacetime becomes granular. Perhaps new dimensions emerge. Perhaps singularities never truly form. At present, nobody knows. That unresolved mystery remains one of the greatest challenges in theoretical physics. Meanwhile, TON 618 continues to sit quietly in the darkness, indifferent to human confusion. Its immense mass bends light. Its horizon hides information. Its interior resists description. The giant black hole has become more than an astronomical object. It has become a crossroads. General relativity leads here. Quantum mechanics leads here. Cosmology leads here. The deepest questions about reality seem to gather around the event horizon like travelers around a fire. And as you contemplate the information paradox, another realization begins to emerge. The mystery of black holes may not be confined to black holes at all. Because beyond TON 618, beyond galaxies, beyond even the visible structure of the cosmos, there are larger puzzles waiting. Invisible puzzles. Puzzles involving missing matter, missing energy, and a universe that appears far stranger than anyone expected. The darkness ahead is vast, but the darkness beyond it may be vaster still. The darkness beyond the black hole opens like a second horizon. For much of this journey, TON 618 has felt like the central mystery. Its mass is staggering. Its event horizon hides entire realms of physics from direct observation. Its existence challenges ideas about how quickly cosmic structures can grow. Yet as you look outward from the shadow, a surprising realization appears. Black holes may not be the biggest mystery in the universe. They may simply be pointing toward it. The glowing quasar fades behind you as your attention shifts to the larger cosmos. Galaxies stretch across the darkness in immense chains and clusters. Vast filaments connect them like threads in a cosmic web. At first glance, the universe appears rich with structure. But when astronomers measure that structure carefully, something peculiar emerges. Most of the universe seems to be missing. Not missing in the sense that it disappeared. Missing in the sense that we cannot see what appears to be there. The first hints appeared nearly a century ago. Astronomers studying galaxies noticed that visible stars did not seem to provide enough gravity to explain observed motions. Galaxies rotated too quickly. Clusters of galaxies behaved strangely. Something unseen appeared to be contributing additional mass. The evidence accumulated slowly, then relentlessly. An established scientific fact is that observations across multiple independent methods strongly indicate the presence of dark matter, an invisible form of matter that interacts gravitationally but has not yet been directly identified. You imagine looking at a galaxy from above. Stars orbit the center much like planets orbit the sun. According to ordinary expectations, stars farther from the center should move more slowly. Instead, many continue moving surprisingly fast. It is as though an enormous invisible structure surrounds the galaxy. Something massive. Something hidden. Something we still do not understand. The surprising observation is that everything visible, every star, planet, nebula, black hole, moon, comet, and cloud of gas, accounts for only a small fraction of the universe's total content. The familiar cosmos is not the majority. It is the minority. You glance back toward TON 618. Even the largest known black hole belongs to that visible fraction. The giant itself may be extraordinary, but it is built from ingredients we at least partially understand. Dark matter remains far more elusive. Scientists have searched for decades. Underground detectors wait in deep laboratories. Particle accelerators probe fundamental physics. Sensitive experiments monitor tiny signals. Yet the identity of dark matter remains unknown. Perhaps it consists of undiscovered particles. Perhaps multiple forms exist. Perhaps some assumption within current models is incomplete. The mystery endures. And then matters become even stranger. Because dark matter is only part of the story. In the late 20th century, astronomers made another startling discovery. They expected the expansion of the universe to slow over time. Gravity should gradually pull everything back together. The expansion might continue forever, but it should at least decelerate. Instead, observations revealed something unexpected. The expansion is accelerating. Galaxies are moving apart faster and faster. Some unknown influence appears to be pushing the universe outward. Scientists call this phenomenon dark energy. The name sounds dramatic. In truth, it is largely a label for ignorance, a carefully measured ignorance, a mathematically constrained ignorance, but ignorance nonetheless. An established fact is that observations of distant supernovae, galaxy distributions, and the cosmic microwave background all support the conclusion that cosmic expansion is accelerating. What causes that acceleration remains uncertain. Dark energy may represent a property of empty space itself. It may reflect a cosmological constant, an idea Einstein once introduced for entirely different reasons. Or it may point toward new physics not yet discovered. Nobody knows for certain. You drift through the cosmic web. Galaxies cluster into enormous structures stretching across hundreds of millions of light years. Between them lie gigantic voids, regions so empty they feel almost impossible. If the Milky Way were reduced to the size of a coin, some cosmic voids would still span continents. The universe alternates between extraordinary richness and extraordinary emptiness. A pattern you have seen before. Stars separated by vast distances. Atoms separated by mostly empty space. Galaxies separated by immense voids. Reality seems strangely economical, using very little to create very much. Yet hidden within that apparent simplicity are mysteries layered upon mysteries. Some observations remain particularly intriguing. Astronomers occasionally encounter gravitational anomalies that resist easy explanation. Structures that appear larger than expected. Regions that move in unusual ways. Signals whose origins remain debated. Most eventually find explanations. Some do not. One example involves the so-called Great Attractor, a gravitational influence affecting the motion of many nearby galaxies. Researchers have learned much about the region over time, but the broader structures involved continue to be studied. Elsewhere, enormous galactic formations challenge assumptions about how matter organizes itself on the largest scales. Most observations fit current cosmological models remarkably well. Yet the universe retains a talent for surprises. Every generation discovers something unexpected. Every generation inherits unanswered questions. And that brings you back to black holes. Because some researchers have wondered whether connections exist between these cosmic mysteries. Could dark matter influence black hole formation? Could primordial black holes contribute to dark matter? Could black holes help reveal new laws governing spacetime? These possibilities remain speculative. Observations have not yet provided definitive answers. But the questions themselves reveal how interconnected modern cosmology has become. Nothing exists in isolation. Not galaxies. Not dark matter. Not black holes. Not even time itself. The universe behaves less like a collection of separate objects and more like a single unfolding system. A vast network of relationships stretching across cosmic history. You pause within that realization. Ton 618 now seems almost symbolic. A giant shadow standing at the crossroads of many mysteries. The black hole is enormous. Yet it occupies a universe dominated by things we cannot directly see. Dark matter shapes galaxies. Dark energy shapes cosmic destiny. And both remain largely unexplained. The deeper scientists look, the stranger the cosmos becomes. What began as a journey toward the biggest black hole ever discovered has transformed into something broader. A journey into the unknown foundations of reality. And somewhere ahead, beyond dark matter, beyond dark energy, beyond even the first galaxies, another question waits. If giant black holes existed astonishingly early in cosmic history, what was happening near the beginning itself? The answer may lie close to the birth of time, or perhaps beyond it. You turn your attention away from the present universe and begin looking backward, far backward, past the galaxies, past the clusters, past the giant filaments of the cosmic web, past even the oldest stars. The farther you look into space, the farther you look into time. And eventually, every journey through astronomy becomes a journey into origins. The great shadow of TON 618 remains somewhere behind you, but its existence now points toward an even deeper puzzle. How did something so massive appear in a universe that was once so young? To answer that question, you must travel toward the beginning, or at least as close to the beginning as modern science allows. The universe around you grows younger. Galaxies become smaller. Stars become rarer. Heavy chemical elements become less common. Everything appears simpler, less structured, less mature. You continue drifting through billions of years of cosmic history. Eventually, the familiar galaxies disappear altogether. Now you arrive at an era when the first stars are only beginning to ignite. The darkness here feels different, not empty, expectant, like a stage before the performance begins. An established scientific fact is that the early universe contained almost no heavy elements. It consisted primarily of hydrogen and helium produced during the first minutes after the Big Bang. Everything else came later. Carbon, oxygen, iron, gold, the calcium in your bones, the oxygen you breathe, the atoms that make up every living thing. All were forged inside stars long after the universe began. In a very literal sense, you are made from cosmic history. The realization never becomes less remarkable. You continue moving backward. The first galaxies shrink into faint collections of gas. The first stars flicker into existence. These pioneering stars were unlike most stars today. Many may have been enormous, hundreds of times the mass of the sun. They lived fast, burned fiercely, and died quickly. Some collapsed into black holes. Scientists suspect these early stellar remnants may have provided seeds for larger black holes later on. Yet a problem remains. The numbers often refuse to cooperate. Even with rapid growth, some ancient quasars appear surprisingly massive. Too massive. Observations reveal giant black holes existing when the universe was only a small fraction of its current age. The surprising observation is that astronomers can detect quasars powered by billion solar mass black holes less than a billion years after the Big Bang. From a cosmic perspective, that is astonishingly early. It is as though nature skipped several chapters of development. The question becomes unavoidable. Where did the first giant black holes come from? Several possibilities compete for attention. One idea involves direct collapse black holes. Instead of forming through ordinary stars, enormous clouds of gas might have collapsed almost directly into massive black holes. Such objects would begin their lives far larger than typical stellar remnants. That head start could help explain later observations. Another possibility involves exceptionally efficient growth. Perhaps early black holes consumed matter at rates higher than expected. Perhaps dense young galaxies supplied abundant fuel. Perhaps mergers occurred frequently enough to accelerate growth dramatically. Each scenario has strengths. Each faces challenges. No explanation has fully solved the puzzle. And that uncertainty leads you even farther back. Soon the first stars vanish entirely. The universe becomes a dark sea of cooling gas. No galaxies. No planets. No black holes. At least not yet. Ahead lies one of the most important relics in all of science: the cosmic microwave background. Imagine a photograph taken when the universe was only about 380,000 years old. That photograph exists, not in visible light, but in faint microwave radiation filling the cosmos. Astronomers have mapped it with extraordinary precision. Tiny variations within that ancient glow reveal the seeds from which later structures formed. Galaxies, clusters, superclusters. Eventually, perhaps even monsters like TON 618. The cosmic microwave background provides one of the strongest pieces of evidence supporting modern cosmology. It allows scientists to study the infant universe directly, and what it reveals is remarkable. The early cosmos was incredibly uniform. Not perfectly uniform. Tiny fluctuations existed, but overall, matter was distributed with astonishing smoothness. From those slight irregularities emerged everything that followed. Every galaxy, every star, every black hole, every living creature. You float before that ancient light, and another mystery appears. Because even the cosmic microwave background is not the beginning. It is merely the earliest light we can currently observe. Before that epoch, the universe remained opaque. Photons scattered constantly. Light could not travel freely. The deeper past remains hidden. A kind of cosmic horizon, not unlike the event horizon of a black hole. Beyond it, observation gives way to inference. Theory takes over. Mathematics becomes the guide. Scientists believe the universe underwent a brief period of extraordinary expansion known as cosmic inflation. According to the inflationary model, space itself expanded at an astonishing rate during a tiny fraction of a second after the Big Bang. This idea helps explain several observed features of the cosmos. Yet the mechanism driving inflation remains uncertain. What caused it? What came before it? Did anything come before it? The questions remain open. Some hypotheses suggest inflation may occur repeatedly in different regions of a larger cosmic structure. Others propose entirely different frameworks. Evidence currently supports inflation's consequences more strongly than its ultimate cause. The mystery persists. You continue approaching the earliest moments accessible to scientific understanding. Time itself seems fragile here. The familiar distinctions between past and future feel less secure. Temperatures rise. Densities increase. Known physics becomes increasingly difficult to apply. And eventually you arrive at a boundary. Not necessarily a physical boundary. A boundary of knowledge. A place where equations lose certainty. A place where current theories stop providing reliable answers. A place surprisingly similar to the center of a black hole. That resemblance has not gone unnoticed. Some researchers have wondered whether deep connections exist between black holes and the birth of the universe. These ideas remain speculative. Observations do not currently establish such links. But the parallels are intriguing. Both involve horizons. Both involve extreme gravity. Both challenge the limits of known physics. Both conceal crucial information. And both remind us how much remains unknown. You look into the ancient darkness. TON 618 began this journey as the largest known black hole. Now it appears as part of a much larger story. A story reaching back toward the first stars. Toward inflation. Toward the birth of spacetime itself. and perhaps toward questions even deeper than origins. Because once you ask how the universe began, another question inevitably follows. Why does a universe exist at all? That question waits ahead, beyond astronomy, beyond physics, in the quiet territory where science meets philosophy. The question hangs in the darkness. Why does a universe exist at all? For most of this journey, the mysteries have felt tangible. Black holes, galaxies, dark matter, ancient light from the early cosmos. These are things scientists can observe, measure, calculate, and debate. But now the path becomes quieter. The questions become larger. And strangely, the larger they become, the less certain the answers seem. You drift in a vast region of imagination somewhere between the beginning of time and the edge of knowledge. The glow of distant galaxies is faint now. Ton 618 has become a memory behind you, though its shadow still influences everything that follows. Because black holes force us to confront questions that are not merely scientific. They are philosophical. The event horizon hides information. The singularity challenges understanding. Time behaves differently near extreme gravity. Space bends. Cause and effect become less intuitive. Eventually, you find yourself wondering not simply how reality works, but what reality actually is. An established scientific fact is that time does not flow identically for all observers. Relativity has demonstrated this repeatedly through experiments involving clocks, satellites, and high-speed particles. At first glance, this sounds like a technical detail. Yet think about its implications. Most human beings instinctively imagine a universal present moment, a single cosmic now. But modern physics suggests the universe may not contain such a thing. Events that appear simultaneous to one observer may not appear simultaneous to another. The present becomes less absolute than everyday experience suggests. This realization can feel unsettling, or beautiful, depending on your mood, and perhaps whether you have had enough sleep. At bedtime, however, it invites wonder. You imagine two travelers crossing the cosmos. Each follows a different path through spacetime. Each experiences a different sequence of events. Each carries a different clock. Reality accommodates both stories. The universe seems less like a fixed stage and more like an intricate tapestry woven from countless perspectives. Then another question arises. What exactly is time? Physicists can measure it, define it operationally, describe how it behaves. Yet its fundamental nature remains surprisingly elusive. Why does time appear to move forward? Why do memories point toward the past rather than the future? Why does entropy, the tendency toward increasing disorder, seem to provide a direction to experience? These questions remain active areas of inquiry. The surprising observation is that many of the laws of physics function almost equally well whether time runs forward or backward. Yet your experience clearly does not. You remember yesterday. You do not remember tomorrow. Somewhere between physical law and conscious experience lies another mystery. And consciousness itself introduces even more questions. You pause among the stars. For billions of years, the universe contained no observers, no minds, no questions, no curiosity. Hydrogen drifted through space. Galaxies formed. Stars ignited. Black holes grew. The cosmos evolved in silence. Then eventually, on at least one small planet, matter began asking questions about itself. The idea is astonishing. Atoms forged inside ancient stars organized into living systems capable of studying stars. The universe became aware of a tiny piece of itself. Scientists continue investigating consciousness through neuroscience, cognitive science, and related fields. Important progress has been made. Yet a complete explanation remains elusive. How subjective experience emerges from physical processes remains one of the deepest unresolved questions in science and philosophy. You do not need consciousness to understand black holes. But black holes often lead people toward questions about consciousness, because both involve hidden interiors, observable effects, and mysteries that resist direct access. You continue drifting. Ahead stretches a universe so large that even its total size remains uncertain. Is space infinite? Nobody knows. Observations indicate that the observable universe extends roughly 93 billion light-years across. But that is merely the portion from which light has had time to reach us. The full cosmos could be vastly larger, possibly infinite, possibly finite but unbounded. Current observations do not provide a definitive answer. Imagine traveling forever through space. Would you eventually return to your starting point? Would the universe continue endlessly? Would entirely new regions appear beyond every horizon? The answers remain hidden. Much like the interior of a black hole, you notice a pattern. Again and again, reality presents horizons. The event horizon of TON 618. The horizon of the observable universe. The horizon separating known physics from quantum gravity. The horizon between objective description and subjective experience. Knowledge expands. Yet boundaries remain. Perhaps that is unavoidable. Perhaps every answer naturally creates new questions. The history of science certainly suggests as much. Newton explained gravity and revealed deeper puzzles. Einstein explained gravity differently and revealed deeper puzzles still. Quantum mechanics solved old mysteries while introducing new ones. Each breakthrough expanded understanding. Each also exposed fresh unknowns. Knowledge grows. Mystery grows with it. You recall the information paradox from earlier. The possibility that information never truly disappears. That idea carries unexpected philosophical weight. If information is fundamental, what does that imply about reality? Some theoretical frameworks increasingly describe the universe in informational terms. Not because reality is literally a computer simulation. There is currently no evidence establishing such claims, but because information appears deeply woven into physical law. Quantum systems store information. Black holes appear connected to information. Entropy relates to information. The concept surfaces repeatedly. Whether this points toward something profound or merely reflects useful mathematics remains uncertain. Yet the pattern is difficult to ignore. The cosmos may be stranger than matter and energy alone. You drift in silence for a while. Galaxies shine softly in the distance. Black holes lurk unseen among them. Quantum particles flicker within fields that permeate space. Time continues its mysterious flow, and the oldest philosophical questions remain remarkably alive. Why is there something rather than nothing? Why do the laws of physics possess the form they do? Can reality ultimately be understood? Or will every explanation reveal deeper layers beneath it? Science does not currently answer these questions completely. Perhaps one day it will illuminate more of them. Perhaps some will remain forever beyond reach. Either possibility is remarkable, because either way, the universe remains larger than any single explanation. And somewhere ahead, beyond all theories and all questions, waits the future itself, the ultimate fate of stars, of galaxies, of black holes, of time, of everything. You look toward the future, not tomorrow, not next year, not even the next billion years. You look beyond civilizations, beyond galaxies, beyond the familiar age of stars. The universe stretches ahead like an ocean of time so vast that ordinary history disappears within it. Ton 618 still exists somewhere behind you, its immense shadow anchored in memory. Yet even the biggest known black hole is not permanent. That realization feels strange. Mountains seem permanent. Planets seem permanent. Stars seem permanent. Black holes feel even more permanent than stars. But the universe rarely grants permanence. Given enough time, almost everything changes. You begin your journey forward. The stars around you continue shining for a while. Galaxies remain crowded with light. New generations of stars form from vast clouds of gas and dust. Planets continue assembling. Perhaps life appears elsewhere. Perhaps countless civilizations emerge and vanish. The universe remains active. For now, an established scientific fact is that stars possess finite lifetimes determined largely by their masses. Massive stars burn through their fuel quickly, while smaller stars can survive for trillions of years. Time passes. Millions of years become billions. Billions become trillions. The familiar constellations disappear. Galaxies evolve. Collisions reshape entire regions of space. The Milky Way and the neighboring Andromeda galaxy eventually merge into a larger system. From the perspective of cosmic time, even galaxies are temporary arrangements. You continue drifting forward. The bright era of star formation gradually slows. Gas supplies diminish. The easiest stellar fuel becomes increasingly scarce. Fewer new stars appear. The universe begins to age. And here comes one of the most surprising observations in all of cosmology. The longest-lived stars may survive for trillions of years, far longer than the universe has existed so far. Humanity currently inhabits what may be considered an early chapter of cosmic history. Not the middle. Not the end. The beginning. The thought is astonishing. Everything that has ever happened on Earth occupies only a tiny fraction of the universe's potential future. Entire ages remain unwritten. You continue onward. Eventually, even the longest-lived stars begin fading. Galaxies grow darker. White dwarfs cool. Neutron stars drift silently through space. Black holes become increasingly important, including giants like TON 618. By now, many familiar structures have vanished. The night sky no longer resembles the one you know. The cosmos enters a quieter era. Some physicists call this the degenerate era, a time dominated by stellar remnants, a time when bright new stars become rare. The universe grows dim. Yet the story continues. Because black holes remain. Ton 618 still endures. Its immense mass grants it extraordinary longevity. Matter occasionally falls inward. Gravity continues bending spacetime. The giant survives while countless stars disappear. But not forever. You remember Hawking radiation. That faint quantum process introduced earlier. Over unimaginable spans of time, black holes slowly lose energy. The effect is tiny. For TON 618, incredibly tiny. Yet cosmic patience exceeds human comprehension. Eventually, even giants must yield. The exact timescales involved are so enormous that writing them out hardly improves understanding. Numbers cease functioning as intuition. What matters is the principle. The black hole evaporates. Very slowly. Very gradually. But inevitably according to current theory. This possibility remains one of the most haunting ideas in modern science. The largest black hole ever discovered. The mightiest gravitational structure in this story. Gone. Not destroyed dramatically. Not shattered. Simply fading away through the patient workings of quantum physics. And after that, the answer depends upon mysteries not yet solved. Current models suggest several possibilities. If dark energy continues behaving as it does today, cosmic expansion may continue indefinitely. Galaxies beyond local gravitational groups eventually disappear beyond observable horizons. The visible universe grows increasingly empty. Stars die. Black holes evaporate. Matter decays perhaps. Energy spreads ever more thinly. A state sometimes called heat death gradually emerges. This scenario represents one leading possibility. Yet uncertainties remain. The nature of dark energy is still unknown. Its future behavior cannot be predicted with complete confidence. Could acceleration change? Could new physics emerge? Could entirely unexpected processes alter cosmic destiny? The unresolved mystery remains profound. The fate of the universe depends partly upon ingredients we still do not understand. Dark matter, dark energy, quantum gravity. The same unknowns encountered throughout this journey continue shaping the ending, which means the ending remains unwritten. You drift farther into the future. Galaxies become isolated islands in a vast expanding darkness. Then even those islands fade. The cosmos grows quiet, almost unimaginably quiet. No bright stars, no glowing nebulae, no bustling galaxies, only sparse remnants scattered across enormous distances. And yet something beautiful remains. The laws of physics continue operating. Quantum fields continue fluctuating. Particles continue interacting. Reality continues existing. The universe does not end in a dramatic explosion. It simply changes. Again. As it always has. You think back to TON 618. To the first sight of its enormous shadow. To the event horizon. To the information paradox. To dark matter and dark energy. To the first stars and the first moments after the Big Bang. Every mystery remains connected. The biggest black hole ever discovered began as the focus of the story. Now it appears as one thread in a tapestry extending across all cosmic history. A clue rather than a conclusion. A doorway rather than a destination. And as you continue floating through the immense future, one final realization emerges. The greatest mysteries are not merely about objects. They are about limits. The limits of observation. The limits of explanation. The limits of knowledge. Those horizons have accompanied you from the beginning. And one waits ahead still. The final horizon. The one beyond which certainty fades into wonder. You arrive at the final horizon. Not a physical boundary. Not an event horizon like the one surrounding TON 618. Not the edge of the observable universe. Not the beginning of time. Not the end. This horizon is something subtler. It is the place where knowledge meets mystery. And despite everything you have seen, you remain standing there. You began beside the largest black hole ever discovered. A gravitational giant capable of reshaping the paths of light itself. A darkness so immense that entire solar systems could disappear within regions that, on cosmic scales, barely register as more than a shadow. At first, it seemed like the destination. Now it feels more like a signpost, because every answer it offered revealed another question behind it. You learned that black holes emerge naturally from gravity, then wondered how they become so enormous. You learned about event horizons, then wondered what happens beyond them. You learned about Hawking radiation, then encountered the information paradox. You explored dark matter, then dark energy. You traveled backward toward the first stars, then toward cosmic inflation, then toward questions about existence itself. Each mystery opened another door, and every door led deeper into the unknown. That pattern may be one of the most important discoveries humanity has ever made. The universe is understandable, yet never completely understood. Those are not the same thing. Science works. Its predictions guide spacecraft across billions of kilometers. Its equations describe stars, galaxies, atoms, and black holes with astonishing accuracy. An established scientific fact is that modern physics has successfully explained enormous portions of the observable universe through testable theories and observations. And yet, despite those triumphs, some of the deepest questions remain unanswered. What is dark matter? What is dark energy? What occurs inside a black hole? How does quantum gravity work? Why do the laws of physics possess their particular form? Why does anything exist at all? The list remains surprisingly long, and perhaps surprisingly beautiful, because mystery is not a sign of failure. It is evidence that discovery remains possible. You look once more toward TON 618, far away now, almost lost among the galaxies. Its immense darkness appears peaceful, silent, patient. It has likely existed for billions of years. It may continue existing for incomprehensible stretches of future time. Yet even it does not possess all the answers. The biggest black hole ever discovered remains, in many ways, an unanswered question written across the cosmos. You imagine future astronomers, future civilizations, perhaps descendants of humanity, perhaps minds entirely different from anything Earth has produced. They build instruments beyond current imagination. They map spacetime with extraordinary precision. They solve mysteries that today seem impossible. Maybe they finally understand dark matter. Maybe they uncover the nature of quantum gravity. Maybe they explain how the first giant black holes formed. Maybe they discover entirely new puzzles waiting beyond those answers. History suggests they will, because every generation inherits mysteries from the previous one, and leaves new mysteries for the next. The chain continues. Knowledge grows. Wonder grows with it. You drift quietly through the darkness. Around you shine the stars. Beyond them, galaxies. Beyond them, more galaxies still, each containing countless suns, countless planets, countless possibilities. Somewhere among them lurk black holes large and small, some ordinary, some extraordinary, and perhaps somewhere, hidden beyond current observation, objects stranger than anything humanity has yet imagined. The universe has surprised us before. There is little reason to believe it has finished. The darkness around you no longer feels threatening. It feels spacious, a place where questions can exist without immediate answers, a place where curiosity matters more than certainty, a place where mystery remains alive. And now, as this long journey slows, the vast cosmic story begins to soften. The galaxies drift farther apart. The brilliant quasars fade into the distance. The immense shadow of TON 618 becomes one lightless point among countless wonders. The universe grows quiet, not empty, just calm. And in that calm, you allow yourself one final look. You see stars being born within glowing clouds. You see galaxies turning through the darkness like great celestial wheels. You see black holes bending spacetime around hidden interiors. You see quantum particles flickering into existence and vanishing again within the restless vacuum. You see cosmic time stretching backward toward the first moments after the Big Bang and forward toward futures beyond imagination. Everything connected. Everything changing. Everything part of the same unfolding story. For a brief moment, the scales all seem to overlap. The smallest quantum fluctuation. The largest galaxy cluster. The deepest black hole. The oldest light. The newest star. All sharing the same universe. A universe that has spent nearly 14 billion years transforming itself. A universe capable of producing atoms, stars, planets, life, curiosity, and questions. A universe capable of producing observers who wonder about black holes while lying comfortably in bed beneath a small sky on a small world. And perhaps that is among the most remarkable facts of all. You never fully solved the mystery of TON 618. You never crossed its horizon. You never discovered what lies at its center. The original question remains. What truly happens beyond the event horizon? Tonight, it remains unanswered. Yet that uncertainty no longer feels frustrating. It feels appropriate, because the story was never really about reaching the end of the mystery. It was about learning how vast the mystery truly is. The stars continue shining. The galaxies continue turning. Black holes continue guarding their secrets. Quantum particles continue dancing through invisible fields. Cosmic time continues flowing through a universe that is both deeply understood and profoundly mysterious. And somewhere, far beyond the reach of any telescope, beyond every horizon we know, beyond the boundaries of present understanding, more secrets wait in silence. Waiting, patiently, as they always have, as they always will. For now, the universe remains what it has always been, partly known, partly hidden, a place where knowledge illuminates the darkness without ever completely removing it. And as the last distant starlight glimmers across the cosmic ocean, you simply float there for a while, listening to the silence, watching the galaxies, remembering the black hole, feeling the slow passage of cosmic time, and resting comfortably between understanding and mystery. The stars grow softer, the galaxies more distant, the black holes quieter, the quantum world gentler. The ages of the universe pass like a slow breath. Nothing rushes. Nothing demands an answer. The cosmos simply continues, endlessly unfolding, endlessly surprising, endlessly beautiful. Slow fade out. Now the journey becomes still. You watch the stars one last time. Tiny points of light scattered across immense darkness. Some are young. Some are ancient. Some may already be gone, their final light only now arriving after long voyages across space and time. Beyond them drift entire galaxies, each carrying billions of suns through the cosmic night. Their spirals turn slowly, so slowly that even millions of years barely reveal the motion. And among those galaxies, hidden from sight, wait the black holes. Silent, invisible, patient, The great shadow of TON 618 remains somewhere in that darkness, surrounded by the faint glow of matter and the curvature of spacetime. Not a monster, not a villain, simply part of the universe's story. One mystery among many. Far below that grand scale, quantum particles continue their restless dance, appearing, interacting, transforming, building the foundations of stars, planets, oceans, living things, and wondering minds. The smallest scales and the largest scales remain connected in ways we are still learning to understand. And overhead, cosmic time stretches onward, past tomorrow, past civilizations, past stars, past galaxies, into futures no one has seen. The universe continues unfolding, page after page, long after every question asked tonight. Some mysteries may one day be solved. Others may remain forever beyond reach. But that is part of the beauty. We understand far more than our ancestors ever imagined. Yet the deepest secrets still wait beyond the horizon. The stars continue shining. The galaxies continue drifting. The black holes continue keeping their silent watch. The quantum world continues whispering beneath everything. And cosmic time carries it all gently forward. So let the darkness become peaceful. Let the questions settle softly. Let the universe remain vast. And let yourself drift quietly among the stars.